Hello, my name is Daniel Jilic, and I'll be presenting on creating low and high pass filters in the Fourier domain. This will build on some of the previous knowledge from the course, like general knowledge about image filtering, as well as how images encode frequency information, and of course, Fourier transforms in general. So, high and low pass filters are essentially emphasizing the respective category of frequencies. So, high pass filters will emphasize high frequencies within the image, while they'll reduce the lower frequencies, and vice versa for low pass filters. We've studied some of these, such as the Laplacian filters, which is a high pass filter. So, this one is generally going to be more of an edge emphasizing one because edges are high frequency information. Whereas a low pass filter, like the Gaussian that we've studied, will tend to emphasize the lower frequency information that's sort of spread out over a greater spatial area. And so this will have the effect of blurring it. And so in creating high and low pass filters in the frequency domain, the most important thing to remember is that the equivalent of doing convolution in the spatial domain is multiplication in the frequency domain. So, whereas if we were to apply a high and low pass or low pass filter in the spatial domain, which is certainly possible, we've done it in the class, we use convolution of the mask on the original image. But if both the mask and the image are transformed into the frequency domain, then the two will simply be multiplied together. And I'll go into more detail on the specific steps of doing this. The first step is to transform the image into the frequency domain using the discrete Fourier transform. The next step will be to create the desired mask for the filter you want to apply to the image. So, for example, if you want to do Gaussian filtering, you'll create a Gaussian mask of the same size as the image, and it should be centered on the origin 0, 0. So this means that when you're actually making this mask, for example, with the Gaussian, the Gaussian mountain, if you will, which should normally be on the center, will actually be split in four so that the peaks will sort of meet at the four corners of the image. The next step will be to transform that mask into the frequency domain by using the discrete Fourier transform, just as you did for the image. As I mentioned before, because multiplication is the equivalent of convolution when you're in the frequency domain, you'll now multiply the image in the frequency domain by the filter in the frequency domain. And now to get back into the spatial domain, you simply take the inverse Fourier transform of that result, and you will now have your filtered image. This is an example of creating a Gaussian filter in the Fourier domain using the steps that were just described. This code is just a version of the code that was gone over, and I think it was the second enrichment session that I modified slightly. The first step, as mentioned, is to take the discrete Fourier transform of the image. The image is held in the variable complex in this example. The next step is to create the Gaussian mask, and this needs to be the same size as the image, but centered on 0, 0. The next step is to take the discrete Fourier transform of that mask, and once that's complete, you can simply multiply those two Fourier transforms. That gives you the result, which here is shown in product. And once you've done that, you can simply take the inverse discrete Fourier transform and you'll have the image filtered using the Gaussian filter. Here's a demonstration of using that Gaussian filter that was coded up on the last slide. On this image here on the left, this came from the Olympus dataset. As you can see, the end result is simple application of a Gaussian filter. Most of the high frequency information, that is the edges, which this image has a lot of, it's basically a grid, you can see that that's all been blurred out. And the overall image is very blurry in general, and there's almost no edges left. Here's the actual intermediate steps of creating that mask. So here's the original discrete Fourier transform of the image itself. You can see a decent amount of higher frequency information here that would correspond to the edges. Which there are plenty of with this grid pattern. Here's the discrete Fourier transform of the Gaussian mask. You can see that there's the little Gaussian mountain at the center, and then everything else is pretty much zero. So when we multiply these together, you're multiplying most of these higher frequencies by a very low value, or even zero itself. And so the result here is the magnitude of that multiplication. You can see that most of the high frequency information is gone. And so all that information towards the corners of this is going to be those edges and other sharper information. And so by taking the inverse Fourier transform of this, we get this image. So finally, I wanted to show an example of what a high-pass filter would look like in the Fourier domain. So this is an example of a discrete Fourier transform of a Laplacian mask. As you can see, it's basically the opposite of the Gaussian mask, where the Gaussian mask was multiplying the high-frequency regions towards the edges of the magnitude image. The Laplacian mask is multiplying the low frequency areas here near the center by low values closer to zero. So these will get minimized, whereas the higher frequencies here in the Fourier domain towards the edges will mostly be retained. So this will have the effect of emphasizing those higher frequency regions.